Okay. So last week I haven't finished yet the proof of the theorem expansion using two rows, and well, I think I have give a precise expression, the precise statement of a theorem. So now I would like to show here. So we assume that they are determinant function okay on M-2 by M-2 matrices, on M-1 by M-1 matrices, and on n times n matrices. Right? And the lecture so we let A is an M by M matrix. So then for we select two rows with index I and j, and we assume the index row index I is less than row index j, row index k. Then so the nth determinant function I deliberately to denote it as a determinant function for M times M matrices. Okay, will be expanded in the following way. So by using two rows, the I0 and the K0, so the entries, this is in the ith entries, and this is in the K, the entry in the I0, and this is the entry in the K0. Okay. And checking the column index J and L. And here, specifically, we ask the column index J is less than the column index L. And the Kj, right? So we just exchange the order of J and L here, and using a determinant function for n-2 times n-2 matrices, Mik and JLA. Okay, and so last week we defined that MIKJL is a function to transform an n times m matrix A to an m-2 times m-2 matrix by deleting the I0, the K0, and the jth column, lth column. Okay, so we delete two rows of A, we delete two columns of A. And so that the resulted matrix has dimension m-2 times m-2. All right, and because that, the determinant function we used is a determinant function for m-2 by m-2 matrices. Okay, so we have this one. Okay, and so I will not repeat what we have done last week. So I just want to write it down at up to here. So we have so far we have, okay, so we are able to reduce the computation of the determinant of the n by n matrix A into the following sum. Okay, so we have reduced the computation of this determinant into the summation of the computation of determinant function on these two special types of matrices, and where we know that so we know we can express the matrix A by their rows. So say x R1 up to Ri up to Rk up to Rn, right? Okay, if A is here, then what is A? Ik, Ej, El. Well, you will replace the ith row of A, Ri by Ej. Ej is just the J's standard unit vector, okay? And you replace the cache row of A by El, okay? So what is that? This is R1, but this is Ej, this is El, and this is Rn. Okay, so this is the ith row. This is the cache row. Okay, and so we have. So last time we have. Okay, right. So this is ith row. So the ith row is Ej. So the one, the non-zero one, is in the jth row, and for the in the jth row, in the jth column here, and for the cache row is El. So the ls component is in the ls row here. So we have one here, okay, right? And the all entries in the ith row are all zeros, the same. And the last time we said that we can use the replacement row operations to eliminate all the non-zero entries above and below this entry, this one, okay, by elementary the replacement row operations, and we call this one to be B, Ij, and the KL, which is A11, 0, 0, A1N, 0, 1, 0, 0, 0, 0, 0, and AN1, 0, and the 0, and the ANN here. Okay, so we eliminate all the entries above this one and this one. This is Bij by replacement row operations. Okay, so we have this one. Okay, and how about A, I, K, E, L, and E, J? Well, so now we have R1, and we have EL, EJ, R, N here. And this is the I0, and here is the K0. Okay, and we write down this matrix. So the matrix is we have is A11, that A1J, A1L, A1N, 0, 1, 0, 0, 1, 0, AN1, ANJ, ANL, ANN. Okay? Now look at the position of 1 here. Not like this one, we have off diagonal 1, 1 here. This is because that J is less than L, so L is bigger. Okay, so L is bigger, so it's in here, and J is smaller, so it's there. So again, by replacement, row operations, we can use this one to cancel all the non-zero entries by replacement operations. And the same, we can use this one, this paper, to cancel all the non-zero entries. So now we have B, and we have IL, and the KJ. This is KJ entries. All right, and so we have A11, 0, 0, A1N. And this is AN1, ANJ, ANL, ANN. We have that. Okay. Now, and for now we can move this one goes to this position, and this one goes to this position, the 2, 2 position. This one will go to the 1, 1 position. This one goes to 2, 2 position. How do we do that? Well, you can move this I0 to the first row. Okay, by using I-1 row exchanges. And then you can move this K0 to the second row by K-2 row exchanges. Okay? So that this one, I will go to here. So it will goes to okay. All right. So now by I minus 1 plus k minus 2 row exchanges. All right. So you move up. Okay, and then you use the column exchanges to move this one now in here to the position by j minus 1 column exchanges. And for here now it's in the second row. You use L minus 2 column exchanges. Right? To move this one to this position. So the total number of row exchanges would be I minus 1 plus k minus 2. And total number of column exchanges would be j minus 1 plus L minus 2. So once we move these two entries goes to the 1, 1 position and then the 2, 2 position, then the rest here, then the first row will be 1, 0, 0, 0, 0. The second row will be 0, 1, 0, 0, 0. And the first column will be 1, 0, 0, 0. The second column will be 0, 1, 0, 0, 0. And what left? Well, here will be what? Would be, it's just like you remove the ice. You remove the ice row, the case row, remove the j's column, the s column. So what you have here will be the m, I, k, j, l of A matrix. Okay, so this matrix is here, all right, and by replacement row operations, you get the B matrix, and then you get into this matrix by row exchanges as well as column exchanges. How about this one? A little bit harder. Okay, so if you move the ice row to the first row, okay, so you need I minus 1 row exchanges, okay, plus when you move this one to the second row, you need k minus 2 row exchanges. All right, but if you do so, you need one more row exchanges to exchange the first and the second row, right? So that 0, 1, 0, 0 will be in the first row, and this row will be in the second row. Okay, just like here. Okay, and then you will go, so you need row exchanges, one more row exchanges. And you need j minus 1 plus L minus 2 column exchanges. So that the matrix becomes to the same as this one. M, I, K, J, L of A. Okay, so they end to the same. Any questions? if you don't use one more row exchanges to exchange these two rows, okay, so that after I minus 1 and the k plus k minus 2 row exchanges, you have actually you have 0, 0, 1, 0, 0, 1, 0, and etc. Okay, you have these two. Now, okay, so you may say that, okay, this is the else column, this is the j's column. Okay. The difficulty is that what if j is equal to 1? If j is equal to 1, then by doing column exchanges, you never put this one to up there. Right? So if j is equal to 1, then you have difficulties to move to this matrix like this one. Okay? This is because that the j in here, j index can be as small as 1. But for L, the least possible error is 2. The least possible error is 2. So that without row exchanges, if j equal to 1, then it's impossible to transform this matrix to this one by using column exchanges only. Okay? So that, but if we do the row exchange one more time, if we switch this to row again by one more row exchanges, then the situation will change. This become to 1, 0, 0, 1. Okay? And we move this one, goes to here by j minus 1 column exchanges. So when j is 1, you don't need to do any column exchange. Not necessary, it's 0. Okay? And for this one, when you need L minus 2 column exchange to move one to this 2 position here. Okay, so one more row exchanges will alleviate our difficulties. Okay, so that's why we have that. Questions? Okay, so if no questions, now determinant of A, I, K, E, J, E, L, this is equal to the determinant of, all right? So by replacement row operations, will not change the determinant value, so that this is equal to the B, I, J, K, L, this matrix, okay? But when you do you change this B matrix to this matrix by row exchanges and the column exchanges. Now you have to, so that you have to, every time when you do the exchange, row exchange, our column exchange, you have to change the sign. So how many times you change the sign? Well, would be I minus 1 plus k minus 2 plus j minus 1 plus L minus 2. So you change the sign that many times. And then you have determinant of n of this matrix. Now, 1 plus 2 plus 1 plus 2 is 6. 6 is an even number, so you can eliminate that. So you have I plus k plus j plus L. Now, about this one, now you can apply theorem 4.2.8, okay? Go to the first one, you think about this one. This is 1, and we have a matrix here. Okay? So this matrix becomes to, by using determinant function for m-1 times m-1 matrices. So this is okay. So by theorem 1A there. Okay, and once again we can apply the theorem one more time. This is okay. Again, right? First time. So this is this one. And how about that one? The determinant of AIK, this time is EL and the EJ. All right? And the same as B, IL, and the KJ. Okay? So that the determinant of this matrix is the same as the determinant of this matrix by axiom number 2 for determinant functions. So this is axiom 2. Okay. And then to go there, we need I minus 1 plus k minus 2 plus 1 plus j minus 1 plus L minus 2. Okay, it comes the determinant of n 1, 0, 1. Okay. Okay. And this is by theorem 4.1.1. Again, theorem 4.1.1. All right. So we have minus 1, I plus k plus j plus L plus 1 here. So we have 1 here. And determinant minus 2 of, again, by theorem 4.2.8, we have m, I, k, j, L. Of A. And now we can plug here this one. So that determinant of A equal to the summation. Okay, and the minus 1, I plus k plus j plus L. Okay. Now that, okay. So that these two determinants, right? They have different sign only. Okay, so this is equal to A ij akl and minus ail akj and determinant of minus 2. All right, and we have done. Okay. Any questions? Because the additional one here, you give minus 1, right? So minus 1 is here, already here. Okay, so now we will use the result to prove a lemma. So suppose that we have determinant function for M-2 times M-2 matrices and for M-1 times M-1 matrices. Okay. Then we can build. So suppose we have a determinant function for M-2 times M-2 matrix and a determinant function for M-1 times M-1 matrices. Then we define a function D on n times n matrices. Okay, so we define them. Okay, by using expansion. All right, using row 1. So A1j, 1 plus j, determinant. M1j, A. Right, so we define the function. Okay, and so we use the 1j minus of A. The 1j minus of A, they are M-1 times M-1 matrices. And they have, so we use the determinant function for M-1 times M-1 matrices. Okay, you use to build a function. Okay, to build a function. Okay, so we build a function here. So it's a function on all n times n matrices. It's a function. Then we will show that this function, D, is a determinant function. Okay? So it's a crucial step for us to prove the existence and uniqueness of determinant function. Okay. Okay. Right. So this definition is using expansion, cofactor expansion by row 1, right? In the cofactor expansion by row 1, in that theorem, we assume the existence of a determinant function for n times n matrices. Okay, so in that theorem, we assume the existence there. But we don't know. Up to now, we don't know whether we have a determinant function for n times n matrix in general, right? Up to now, we know we have one and only one determinant function for 2 times 2 matrices. And also, I have written an example. I haven't mentioned yet, but in my lecture notes, it's example 4.2.2, right? In example 4.2.2, I show that there is one and only one 3 times determinant function for 3 times 3 matrices. Okay, and if you read through this example, you will see that if you want to give a direct proof, because you have to verify xm1, xm2, and xm3, right? Especially to verify the xm2 and xm3 will take much effort if the order of matrices become bigger and bigger. For example, in example 4.4.2, you can see that I spent 3 pages, I think, to verify, right, that all possible replacement operation will not change the determinant. And I have shown that all possible scaling will scale the determinant function by the same scalar, right? So actually you can see it's lengthy. And but anyway, I did that, all right, in example 4.2.2. Okay, but we haven't yet proved the existence of a determinant function for n times n matrices. So here, give us a hope that, well, suppose we have a determinant function for lower order matrices. For example, for n minus 2 times n minus 2 matrix, we have one determinant function. And also, we have one determinant function for all n minus 1 times n minus 1 matrices. Then we can define a determinant function by using this expansion formula. This is what I want to show to you. Okay. So any questions? Okay. So all right. So we have to verify the 3 axioms are fulfilled by this function. So of course, how about the first axiom? All right, so we define a delta notation. So delta ij be 1 when I equal to j, and 0 when I not equal to j. So delta ij is just a notation. Okay, this is common definition. You will see this delta notation quite often. Okay, now the 1 minor of the m times an identity matrix, right? So if you delete the first row, delete the first column of the identity, the n times an identity matrix, you will see that it's again the m times 1, n minus 1 times n minus 1 identity matrix. That is easy, right? You see that. All right, so we have, okay, if you like, for example, 4 times 4. If you delete, you see that this is the 3 by 3 identity matrix. Okay, so you can see that is true. Okay, now we evaluate the function value of D at the identity matrix. Now, by definition, So Aij is the entries of their function. And you see that we know that the identity matrix is actually delta ij, right? It's a matrix represented by delta ij, right? Because when I equal to j, you have diagonal entries which are ones. But if I not equal to j, then the entry is 0, okay, by this definition. So this is delta 1j, okay? Minus 1, 1 plus j, determinant of minus 1, and the M1j of identity matrix. Okay? All right, so by definition, this one. Right? So delta 1j is just the 1j entries of the identity matrix. Okay? But delta 1j is 1. If j is not equal to 1, then delta ij is 0. So only one term left. Okay, so you have 1 plus 1, determinant of okay, so the sum has n terms, but because that delta 1j is 0 for j not equal to 1, so you have only one term left. And so this is 1 because the square of minus 1 is 1. So this has become 2. And as we know, the 1 minor of the n times n identity matrix is the n minus 1 times n minus 1 identity matrix. And which is 1 by axiom 1 for the determinant function. Okay? Because dt sub n minus 1 is a determinant function, so it has axiom 1, which is 1, right? So now the function value of d at the m times n identity matrix is equal to 1. Okay, so that's so at x1, axiom 1 is fulfilled by d. All right, so this is the first step, a very simple step to have. Okay, now we will come to a difficult part. Note that. All right, so by the cofactor expansion, okay, of dt minus 1 using rho k minus 1 for any one, let's think. Okay, so we have, okay, remember in this expansion formula, the case row of A when k greater than 1, right? The case row of A becomes to the k minus 1's row in this minor. Is that okay? For A, when you remove the first row and the just column, say just column here. Now the case row. So the second row becomes the first row of, what is this? Okay, so the case row, the second row becomes the first row, the third row becomes the second row, and the first row becomes the third row. So in general, the case row of A becomes to the k minus 1 row of the minors, the M1J minor. Okay, so we expand them using row k minus 1. Okay, for any k, so we can select a k, right? Select a k, arbitrary k, just any k. So now after that, so we will have dA minus 1 plus k plus j plus L, A1j AKL minus A1L AKJ, determinant of M minus 2, and the M1K JL A. Okay. So that the dA can be expressed by this expression by using a determinant function for n minus 2 by n minus 2 matrices. Okay, similar to the procedure in the proof of the previous theorem 4.2.b used to obtain the expansion of a determinant function using two rows. Okay. So it's just like so the procedure is the same. So I will not go through the detail because we have discussed already in the previous theorem. Okay. So that so for each so the determinant function, we will do the expansion. Okay. So each one of them okay, so I will say that the expansion is that okay, so so I will make remark here. Maybe I write here cofactor expansion for the determinant function of minus 1, so that the determinant function of M1J A, okay, okay, so you can do L from 1 to M minus 1, because that this is a matrix of order M minus 1. Okay, and that it's by k, so that So we call this one to be, say, C CUV, for example. Okay, and so we have C K minus 1 L, okay, of L, okay, and the determinant of M 1 K J L A. Okay, but I will see that this is actually equal to, and it's A K L, and it depends on. So it's a little bit complicated, right? Because you have to consider the L is bigger than JL naught, so it's a little bit very complicated there, and so that the procedure will be the same. So this is what we have done. That we just do. Okay, so I think I have to write it properly. So this will be K minus 1 and the L of M 1 J A. Okay. Okay. So you have to do you remove the first row and just column, and then you remove the K minus 1 row and the L's column there. Okay. Right. So this is cofactor expansions. But anyway, we will go through the procedure in the proof of the last theorem, and you end up with the same formula actually. Okay. So that is the formula we use here. Okay. Questions? So I omit the procedure because if I do it, then I will spend at least 30 minutes because that this is the procedure we do the proof of the theorem 4.2.b. Okay. All right. But anyway, we have arrived this one. Okay. So now we use this formula to justify the axiom number 2. Okay, so we let R1, R2, Rn be rows of A, and alpha a scalar. Right? Now, since we have K is greater than 1. Now, so the M1K JL A1 R1 plus alpha RK. Right? So what is this? This is actually, you do the replacement the operation. Okay? You replace the first row of A1 by what? By row 1 plus a multiple of row K. So actually this is the replacement operation that you add a multiple of row K to row 1. Right? So we use A1, the notation here. And but once you do so, when you remove the first row, the case row, the just and also the just column, else column, you find that this is actually the same as 1K JL on A, right? Because that you will remove the first row, right? So the operations, the replacement you have done in the first row, well, will be ignored. Okay, so this case. And this is the same as you do the same thing on if you replace, you do the replacement operation by adding a multiple of R1, row 1 to the row K. Okay? This is because that you will remove the first and kth row. When you remove first and kth row, then row operations on replacement operations on the first row or on the kth row by R1, well, will do nothing, right? It was the same as that one. So any questions? Do I need to explain this fact more? Okay. Well, you can, yeah, all right. This one, the other is okay. Now if you remove these two rows and the columns, you will get will be the same. Okay, so they have the same here. Okay, so this is true for all one. Okay, so now we have now. All right, so when we do the replacement operations by adding a multiple of kth row to the 1st row, okay, and we know this is equal to A1 and R1 plus alpha RK. All right, and by our definition, by the formula here, this is summation one plus K plus J plus L. Now the first row is R1 plus alpha RK, so the entries will be A1J plus alpha AKJ, okay, and AKL minus, because we are expanding this matrix. So the entries will be, for example, the first entries of the first row will be R11 plus alpha, A11 plus alpha AK1, okay, etc. And this one will be A1L plus alpha AKL times AKJ. Okay. And determinant m minus 2 of m 1k JL A1 R1 plus alpha RK. Okay, so it's here. So we just do the expansion. But as we know, this matrix is the same as this matrix, right? So we know this one is equal to M1K JL of A, the same. Okay, and so now, and for here we have, so we do the computation here. When we do the computation, we have A1J AKL minus A1L AKJ plus alpha AKJ AKL minus AKL AKJ. Okay? So this is equal to this one. But when you observe here, this is 0. Because these two terms are equal. So that this is equal to, so this is equal to summation 1 plus K plus J plus L. And here we have A1J AKL minus A1L AKJ. And here is determinant of M minus 2 of M 1K JL of A. Okay. And this is exactly the same as that. So this is dA. Okay. So we prove that if you do this replacement operations on A, you will not change the determinant value. Okay? You will not change them. Okay, now how about you do all right, so now you add a multiple of row 1 to the case row. And so this is D of AK RK plus alpha R1. And by the expansion formula, you have 1 plus K plus J plus L. Now you have A1J, but the case row becomes to an AKL plus alpha A1L minus A1L and AKJ plus alpha A1J. Okay, because the case row has entries which is AKL and multiple of the component in row 1 to add to row K here. All right, and we have determinant minus 2 M1K JL AK RK plus alpha R1. Okay, but as we mentioned before, this one is equal to M1K JL of A already, the same. And when we calculate this part, we find that it's A1 J AKL minus A1L AKJ plus alpha A1J A1L minus A1L A1J. Okay? And you can say they cancel to each other. So we have only this term left. And so this is summation 1 plus K plus J plus L and A1J AKL minus A1L AKJ and the determinant of M minus 2 M1K JL of A. Okay. And again, this is equal to DFA. So again, you will not change the determinant value again. Okay. Okay. Now, the last type is that okay, so if the row replacement row operation does not involve row 1, then we have M1J AK RK plus alpha RM. Okay. All right. So if we do the 1J minor of this matrix, we will find that this is M1J minor of A. All right. But you do the replacement row operation, right? It's K minus 1 row by RKJ plus alpha RMJ. Okay. All right. So where RKJ and RMJ, they are M minus 1 dimensional row vectors. Okay, so obtained from RK and RM, right, by deleting the J's component respectively. So that if you have RK, which is A1, AK1, AK2, up to AKJ, AKN, you delete it. Then you get RKJ, which is just AK1, AKJ minus 1, AKJ plus 1, AKN. Okay, so it's one dimension shorter than the original row vectors. Okay, so that this come to this one. And so that the M minus 1's determinant of M1J AK RK plus alpha RM, okay, is equal to the determinant of function of this matrix M1JA K minus 1 RKJ plus alpha RMJ. Okay. this is saying that you are doing the replacement row operation, all right, on the k minus 1th row of on these minors. So they will not change the determinant value by axiom number 2. So this is equal to okay, go to this one. Okay, so it is crucial to know this one. And so this is by axiom number 2. Okay. Okay, and so finally we are able to, so if we do the replacement row operation, all right, k and m not equal to I, okay? And we know this is equal to d a k r k plus alpha r m. And by the our expansion formula, this is a 1j 1 plus j, because the first row of this matrix will not change. So we use A1j and the determinant of m minus 1 and the m1j of ak rk plus alpha rm. Okay, and but we just proved that this is equal to the determinant of, okay, and this is d of a again. Okay, so we have done for. Okay, so this is say A, B, and C. All right, so by A, B, and C, that axiom number 2 for a determinant function okay, is fulfilled by D. Okay, so, well, it seems that I can't finish the proof. So anyway, this is the most difficult part for this lemma. Okay, so we have justified that the function we define here fulfill axiom number 1 and axiom number 2. So the axiom number 3, that will be simple, and I will finish that on Friday. Okay, so sorry, I stop here, and I think we will have the quiz at 25. Please move quickly, so we will have quiz at 11:25.